Have you ever stopped to think about what happens in that split second after you hit compile and before your program actually runs? There's this crucial step, a kind of magic that happens behind the scenes. It's the work of a hidden mastercrafts person, taking all the scattered pieces of our code and forging them into a single, working program. Today, we're finally putting the spotlight on that unsung hero, the linker. So, here's our game plan. We're going to start by really getting a feel for the linker's role. Then we'll follow our code on its journey from just plain text into these intermediate things called object files. After that, we'll see how the linker plays detective to connect all the dots, how it finds a home for everything in memory, and finally, we'll get into the really cool stuff, the incredible magic modern linkers are pulling off every single day.
All right, let's jump right into our first section, the code's unsung hero. We're asking a simple question. What really happens after you compile your code? You know, we always give the compiler all the credit, but it's the linker that's the true master craftsman here, the one who actually assembles the final product. So let me ask you this. You've written your code, you've compiled it, and hey, no errors. But is it a program? Can you actually run it yet? The answer, which might surprise you, is no, not even close. The compiler just made the bricks. It hasn't built the house yet.
And you know, this isn't some new problem. The idea of linking code together is almost as old as computers themselves. I mean, way back in 1947, they were figuring out how to combine routines from separate magnetic tapes. Since then, linkers have just kept evolving, from managing these crazy complex memory overlays in the 60s to dealing with the absolute madness of C++ templates and shared libraries today. They have always been essential.
That brings us to our second section, where we're going to look at the raw materials the linker actually works with. We're following the journey from source code to something called an object file. This is what the compiler actually spits out.
Okay, so in a typical setup, your source code goes on this little adventure. First, it gets preprocessed, then compiled into assembly code, and then assembled into an object file. But look at the end of the line. The linker is the final crucial step. It's the one that gathers up all these intermediate pieces and forges the final executable program that you can actually double-click and run.
So what the heck is an object file? The best way to think about it is like a single puzzle piece. It's got the machine code from one of your source files, but it's definitely not the whole picture. And the most important part, it's full of unresolved references, which are basically little sticky notes left by the compiler that say, hey, I need to connect to a function over there, but I have no idea where there is yet.
And if we take a peek inside one of these things, like this classic Unix object file, you can see it's got a pretty clear structure. There's a header with some metadata, a text section, that's where the actual machine code lives, a data section for variables, and a bunch of other info that is specifically there for the linker to read. It's a self-contained, but totally incomplete blueprint.
Which brings us right to section 3, connecting the dots. This is the first huge job for the linker, and honestly, it's a lot like detective work. It has to go and solve all those little sticky note mysteries we just talked about.
The linker's main tool for this investigation is something called a symbol. A symbol is really just a name. It could be the name of a function, like printf, or the name of a global variable. Now, for every single time your code uses a symbol, the linker's job is to hunt down the one and only one place where that symbol is actually defined. This whole process, it's called symbol resolution.
Let's use a super simple example to see this in action. Imagine you've got two files. m.c has your main function, and inside it you call another function named a. Now the code for function a lives in a completely different file, a.c. The compiler works on these files one at a time, in total isolation. So when it's compiling m.c, it has absolutely no idea where the code for function a is, or where it's going to end up.
And this is the fascinating result. If we actually crack open that object file from m.c and look at the machine code, the instruction to call function a literally says call 0. The compiler basically just threw its hands up and punted. It put a 0 as a placeholder and left a little note for the linker that says, hey, this is your problem now. You need to figure this out and patch this address later. So the linker has figured out what needs to connect to what. Now it's time for section 4, a place for everything. The linker has to design the final memory map for the whole program and go back and fix all those placeholders. This is called allocation and relocation. Right, so this patching process has a technical name, relocation. It's a two-step dance. First, the linker lays out all the pieces, deciding exactly where every single function and variable will live in the final program's memory. Then, it goes back through all the code and replaces every single one of those call0 placeholders with the real, final memory address. And here is the beautiful after picture. Once the linker has worked its magic, that call0 instruction is gone. It's been transformed. Now it says call 10b4, which is the actual, final memory address that the linker decided to give to function A. Just like that, the problem is solved, the connection is made, and the program is whole. Now, you might be thinking, how can the linker just assign an address? What if something else is already there? Well, the secret ingredient here is virtual memory. The operating system gives every program its own private, pristine, predictable address space to play in. This lets the linker lay everything out perfectly, and then the OS handles the messy, complicated job of mapping those virtual addresses to wherever there's free space in physical RAM. And that brings us to our final section, the modern linker's magic. Because let me tell you, the linker's job has gotten so much more complicated than just patching a few addresses. Today, they are solving some of the absolute trickiest problems in software engineering. A huge piece of the modern puzzle is managing libraries. You've got static libraries, where the linker literally copies and pastes all the library code right into your program. This makes your executable file bigger, but it's totally self-contained. Then you have dynamic or shared libraries, think DLLs on Windows. Here, the linker just leaves a little IOU telling the operating system to connect the program to a single shared copy of that library when it runs. It saves a ton of disk space and memory.
And the list of challenges just goes on and on. Modern linkers have to deal with C++ templates, which can create tons of duplicate code that needs to be found and thrown out. They manage something called thread local storage. They create special position-independent codes so shared libraries can be loaded anywhere. They even do incremental linking to make our builds faster and perform incredible whole program optimizations to make our code faster than the compiler could alone.
Here's a fantastic example of a really thorny problem, often called the malloc hack. What if your main program uses the malloc function to allocate memory, but it also uses a shared library that also needs to call malloc? If they use different versions, you could end up trying to free memory with the wrong allocator, and that's a recipe for a crash. A sophisticated linker can actually step in and ensure that everyone, both your program and the library, agree to use the exact same version of malloc. It's incredibly clever.
It really all comes down to this one crucial point, which is captured perfectly in this quote. The linker is completely unique. It is the only tool in the entire software building process that has a complete, holistic view of your program. It sees every single object file, every library, all at once. And it's this global perspective that gives it the power to perform all these amazing feats of assembly and optimization.
So that leaves us with one last thought to ponder. We've seen the linker evolve from a simple program that loaded tapes into a highly intelligent optimizer. As our software gets even more complex and modular, built from microservices, plugins, and dynamic components, what's the next great challenge that's going to fall on the shoulders of this mastercraft person? What will be the next great act of linker magic?